In this module, we'll be talking about maximum likelihood estimation. So let's just recap where we are so far. We have a data vector y, lowercase y is y1 up to y sub n. We have some covariates that we put into a design matrix X. And then we have an unknown vector of regression coefficients B and an unknown variance parameter sigma squared. And we model the response vector y as multivariate normal with mean vector xb and covariance matrix sigma squared I. Now this assumption means that all of the y's are independent and they all have the same variance sigma squared. So let's look at the probability density function for this multivariate normal distribution. We've seen this once before in the class, but here's the multivariate normal. We have the argument z. This is a vector length n, and this is the formula for the joint probability density function, 2 pi to the minus n over 2. The determinant of the covariance matrix to the minus 1/2 power. And then we have this e to this quadratic form. There's a sigma squared I covariance matrix to the inverse, and then there's z minus xb on both sides. If we take the log, it's just minus m over 2 log 2 pi minus 1/2 log det sigma squared I plus or minus 1/2 that quadratic form. Now, the likelihood function is simply the PDF or joint PDF evaluated at the data vector y viewed as a function of the parameters. So we're going to call that likelihood function capital L. The second part of the definition is we view it as a function of the parameters. The parameters are b and sigma squared. And it's evaluated at the function y. What I mean by that is here we have p argument z. This is like a generic variable. For example, if you integrated this over z, you would get 1. But we're going to plug in a specific value for z, and that specific value is the data vector y. So if we do that, we get this expression here. So the only thing that's changed on the right-hand side of this equation is z is replaced with the data vector y. And the right-hand side of the equation has changed just to drive home the point that we're viewing this as a function of the parameters rather than as a function of y. And then the log likelihood function is just the log of the likelihood function. Now, what maximum likelihood estimation does is it picks the parameters b and sigma squared to maximize this function, big L or little l, as a function of the parameters. So the way to think about this is we've observed some data, and we're picking the parameters that make it so the data has the highest possible probability. Why the maximum? Well, I guess the way it's been put most clearly to me, and I don't know if you'll feel that this is clear or not, is that you wouldn't do minimum likelihood estimation. You wouldn't pick parameters that made the data you observed unlikely. And so if you have a choice between two values of the parameters, you're going to pick the one that has the higher likelihood. And so therefore, why not pick the highest possible one, which is the maximum likelihood estimation? Let's see this in action. So this will be the same usual model that we've seen before. Yi is b0 plus epsilon I, where the epsilons are independent, normal 0 sigma squared. This is an even simpler example because the model has only an intercept and no covariates. So the log likelihood function is the following. Minus n over 2 log 2 pi minus 1/2 log determinant of the covariance matrix. And then the mean vector is B0 times the 1 vector. So it's the quadratic form with that vector. Now, one fact about the log determinant. If you have the determinant of a scalar times a matrix, the determinant of that product is the scalar to the power of the number of rows in the matrix times the determinant of the matrix. So this becomes log of sigma squared to the n times determinant of the identity matrix. The determinant of the identity matrix, since it's a diagonal matrix, is just the product of 1 n times. So that's just 1. So the log determinant of this matrix is log sigma to the 2n, which is n log sigma squared. The other piece we have to compute is the inverse of sigma squared I. The inverse of that matrix is just 1 over sigma squared times I. How do you check that? Multiply that by sigma squared I and verify that you get the identity matrix. So you can check that yourself, but that's an easy one. So if we plug that expression in here, we get a 1 over sigma squared coming out, minus 1/2 here, and this is y minus b0 times the 1 vector transpose. There's an I on the inside, but that goes away because it's the identity matrix. And so this expression is just minus 1 over 2 sigma squared times the residual sums of squares. So this is just the squared length of the vector y minus b0, 1. Okay, so that is the quadratic form part of the log likelihood. Here's the determinant part. So if we put all that stuff together, we just get minus n over 2 log 2 pi. That stays there. This is the log determinant, minus n over 2 log sigma squared. It's minus 1/2 times the log determinant. And this is the quadratic form term. Now to find estimates of the two parameters here, b0 and sigma squared, we take this log likelihood function. Remember that if you want to maximize the likelihood, that's the same thing as maximizing the log likelihood because there's a one-to-one transformation between the two. So we're going to maximize the log likelihood because it's more convenient to take derivatives after you take the log because all the terms separate here. So let's do that. Let's take partial derivatives of this log likelihood function with respect to b0 and sigma squared. So if we take derivatives with respect to b0, that goes away, this term goes away, and we're left with this term. We're going to get plus, we get a minus and a minus. So we'll get plus, the 2 comes out, cancels with that 2. Here I've written it out here. And then you get yi minus b0. So if you put everything together, you have 1 over sigma squared. Sum I equals 1 to n yi minus b0. So that's the first partial derivative with respect to b0. Here we're going to take a partial derivative with respect to the quantity sigma squared. Turns out that's an easier calculation than taking the derivative with respect to sigma. So if we look at this, we have this part goes away. Then we have minus n over 2 log sigma squared. Now derivative of the log is going to be 1 over the thing. So we're going to get minus n over 2 times 1 over sigma squared. That's here. And then take the derivative here. We're going to get plus 1 over 2 sigma to the 4th. So it's like we're taking the derivative. Remember, we're taking derivative with respect to sigma squared. So just think about replacing sigma squared with like x and take derivative with respect to x. Yeah, derivative of 1 over x is minus 1 over x squared. So that becomes 1 over 2 sigma to the 4th. And then this part remains. So if we set both equal to 0, this first one is easy to solve because there's the 1 over sigma squared is outside this sum. So if as long as that's not 0, we can just set multiply both sides by sigma squared, and we get just this thing equals 0, which means the sum I equals 1 to n yi equals the sum I equals 1 to n b0 hat. And the right-hand side is just n b0 hat. So that means b0 hat is 1 over n sum yi. It's just the average. If we do the same thing for sigma squared, we're looking at this equation now. We get n over 2 sigma hat squared equals 1 over 2 sigma hat to the 4th. Multiply both sides by sigma hat squared and rearrange some stuff. You get sigma hat squared equals 1 over n sum I equals 1 to n yi minus b0 hat. Now let's take a second and look at these estimates. b0 hat is just the average of the yi's. That is exactly the same estimate we got when we minimized the sum of squares. So that's our first clue that maximum likelihood is doing something reasonable here. If we look at sigma hat squared, we get something close to what we got when we derived our own unbiased estimate for sigma squared. We get 1 over n sum I equals 1 to n yi minus b0 hat squared. Now, when we did this before, the unbiased estimator was a 1 over n minus 1. So the maximum likelihood estimator is a little bit different. Instead of dividing by n minus 1, we divide by n. So that's a little bit different. All right, so just to summarize that, b0 hat is the same thing as the least squares estimate. So maximizing the likelihood is equivalent to minimizing the residual sum of squares. And sigma hat squared is close, but slightly different. Let's do another example, and this one has covariates. So yi is sum j equals 0 to p, b sub j xij plus epsilon I. This b is the vector where we collect all those regression coefficients. And we have the, didn't write it here, but we have the same assumption on the epsilon i's that the covariance matrix is sigma squared I. The log likelihood, I'm not going through all the steps, but the determinant is going to be exactly the same. If the covariance matrix is the same, it's sigma squared I. So the inverse is going to be the same. And if you do those calculations, you see what you're going to get is, let me actually go up here. So this is the expression. And the inverse of this is 1 over sigma squared times I. So you're just going to get the squared length of the vector y minus xb with minus 1 over 2 sigma squared on the outside. So that's exactly what you get here. Now, if we take derivatives, partial derivatives of this log likelihood function with respect to b0 to bp, we get these expressions here. You can do these on your own, but this is the answer. And if you stare at these equations, these are exactly the normal equations with the 1 over sigma squared out front. So we get something very similar here to what we got before when we minimize the sum of squares. And if we take the derivative with respect to the sigma squared, we get minus n over 2 sigma squared plus the same thing here, minus 1 over 2 sigma to the 4th, sum of the residual sum of squares here. So again, I'm not going through that, but the steps are very similar to the previous one. And if we set the first part, if we set the normal equations to equal to 0, we know what that answer is. We've done this before. B hat equals x transpose x inverse x transpose y. And if we plug in that value for b, and then we set the equation for sigma squared, partial derivative with respect to sigma squared equal to 0, we're going to get this moved to the other side, cancel some sigma squareds, and sigma hat squared equals 1 over n times this sum. So this is the residual sum of squares, and our estimate is 1 over n times the residual sum of squares. All right, so that's great, but what is the point of maximum likelihood if it's giving us essentially the same estimates that we got by doing least squares and finding unbiased estimators for the variance parameter, but it's actually a little bit worse because the variance parameter is now biased if you use the maximum likelihood estimates. So the real power is not these simple cases. The real power of maximum likelihood comes by looking at more complicated situations where it's not exactly clear how you would generate an estimate otherwise. So let's look at one really simple example that's just a kind of a minor twist on what we've seen before. And we'll see that maximum likelihood will gives us an answer, and it's a reasonable answer. So here's the model. yi is b0 plus epsilon I. So that looks the same as what we've seen before. That's just a linear model with intercept. But we're going to make a change to our assumption about the error terms. They're still going to be independent mean 0. But the variance is going to be sigma times xi squared, where xi is some numeric covariate. So this situation is different than what we've seen before. Usually we've been putting the numeric covariate into the expected value part of the model. Here we're putting it into the variance. So we can write down the entire vector of the model for the responses as vector y. We'll write this as b0 times the 1 vector. The expected value is always b0. And the covariance matrix, we're going to just write this as sigma. And we can write out what the covariance matrix is in this convenient form. In R, there's a function called diag. I'm kind of using that R notation here. Writing this as diag sigma squared x1 squared, sigma squared x2 squared, yada, 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 sigma squared xn squared. What I mean by that is the capital sigma is a diagonal matrix, and these are the values along the diagonal. So if we were to write this out in a big matrix, we'd write it like this. This notation means these are the values on the diagonal. Of course, they're multiplied by sigma squared. And then everything off the diagonal is 0. So again, this is something different from before. But maximum likelihood allows us to easily generate estimates for both of these parameters, b0 and sigma squared. So here's the likelihood. This is just the multivariate normal likelihood. I plugged in b01 here, and I'm putting in sigma. Now what we have to do is we have to look at what's the determinant of sigma. Sigma is a diagonal matrix, so the determinant is just the product of the diagonal entries, and that would be sigma squared to the n power multiplied by the product of the x sub i's squared. So the log determinant is just the log of that. That's n log sigma squared plus some log xi squared. If you take the log of a product, it becomes the sum of the log of each term, so it's the log of this times the log of this. The log of this product is the sum of the log, so that's why you get this term here. The inverse, since it's a diagonal matrix, it's easy to calculate the inverse. You get 1 over sigma squared times diagonal matrix with xi to the minus 2. If you want to verify this, just multiply this thing by sigma and check that you get the identity matrix. This means that the quadratic form term is the following. Sigma inverse, we pull out this 1 over sigma squared, so that's here. And then we have y minus b01 transpose. This is the part of this part of the inverse. And if you were to write out this matrix multiplication, you get this thing here. So if you think about this, so you could do this on your own. I won't go through all the steps. First thing is you do this matrix times this vector. What you're going to get is y minus b01 And then you divide each element by x sub I squared. And then you then multiply that resulting vector, do the dot product with this vector, and that will give you this sum here. So this is the quadratic form term. If you put all this stuff together, here is the log likelihood, minus n over 2 log 2 pi, that's always the same, minus n over 2 log sigma squared minus 1/2 sum I equals 1 to n xi squared. This is the log determinant term, and this we just calculated. This is the quadratic form term. Now, if we want to maximize this over b0, that's the same thing as minimizing this expression. And if we look at this, so it's not clear that, so we could figure out what the actual b0 is. That's fine. It's going to have a formula in terms of matrix multiplications. But let's not do that. Let's just look at this as something like least squares. We're trying to minimize this quantity. And this is sort of like least squares. If we didn't have this 1 over x sub I squared, it would be exactly least squares. But it's 1 over xi squared times this thing squared, and then we sum it up. This is called weighted least squares. The reason for that is, like I just said, it's least squares except each term is weighted by 1 over x sub I squared. If we look at the residual term, the term for the partial derivative with respect to sigma squared, if you look at this, that goes away. This is n over 2 times 1 over sigma squared, so that's this. And then here, this part does not depend on sigma squared, and this thing depends on sigma squared in a similar way as to the previous model. So you get 1 over 2 sigma to the 4th times that sum. If you solve this for sigma squared, you get sigma hat squared equals 1 over n sum 1 over xi squared yi minus b0 hat squared. So I think this estimate also makes a lot of sense. Here's the heuristic motivation. The variance of yi minus b0, according to the model, this is the variance of the error term, is xi squared sigma squared. So if you take yi minus b0 and divide by xi, the variance of this thing is sigma squared. So in order to generate an estimate of sigma squared, one thing we could do is take these quantities, 1 over xi y times yi minus b0, square it, add it up, and divide by n, which is exactly what the maximum likelihood estimate does. Again, this is probably going to be a biased estimate, but if n is large, then it should be close to unbiased. Now, we didn't give a formula. Like I said, we didn't give a formula for b0 hat. We wrote it down as the minimizer of a criterion. Like I said, there is a formula, but it's actually easier to write down a general formula that involves covariates, and that's what we're going to do next. So here is our multiple linear model expressed in the most general form we have so far as a multivariate normal distribution. So the vector y, which is our model for responses, is distributed as multivariate normal with mean vector xb and covariance matrix sigma sub theta. So I'm writing down the covariance matrix in a general form. So here the covariance matrix will depend on some parameter or vector of parameters theta. I'll show you an example of that in just a second. And our task here is we just get to observe data vector y and the covariates x, and we want to estimate both b, the regression coefficients, and theta, which are the parameters that determine what the exact covariance matrix is. So the first thing I want to do here is show for what the log likelihood is as a function of b and theta. So that won't change much. But then I'm going to show what are the equations that you need to solve in order to estimate the regression coefficients. So here's the log likelihood. Minus n over 2 log 2 pi. You have the log determinant of the covariance matrix. and then you have this quadratic form. So this should all look familiar. The only difference here is we're plugging in this more general form for the covariance matrix. If we take the partial derivatives of the log likelihood with respect to the regression coefficients, here I'm taking it with respect to b sub k. So this is, let's see, a slight typo here. This should say partial b sub k. And here the sum is over j. So here is the part of the log likelihood that depends on b sub k. So we're actually only looking at the quadratic form part because that's the only part that depends on b. So I've just gotten rid of this because we know the derivative with respect to this part is going to be 0. And here I'm just writing out what the quadratic form is. So remember, a quadratic form is it's going to be a double sum over all entries of the matrix. It's in the middle, so sigma theta inverse entry IL. And then we're looking at the I entry of this one and the L entry of this one here, y minus xb. So this is the I entry, yi minus sum j equals 0 to p. This is the matrix multiplication xb, looking at the ith entry of that vector. And here's the same thing, but for the lth entry, y sub l minus sum j equals 0 to p x lj bj. So this is just the summation form of the quadratic form. And this is a type of, this should say b sub j. So, sorry, b sub k. So we're taking the derivative of this expression with respect to b sub k. So there's, it's a double sum, so the derivative is going to be the sum of the derivatives. And then b sub k appears in two places. It appears here and it appears here. So we just use the product rule for derivatives. So we're going to get two terms. The first one is going to be this times the derivative of this times this. And the second one is going to be derivative of this times this times this. So if we look at the derivative of this part, the thing that survives is going to be xlk. That's the one that multiplies b sub k. So one of these is the kth one. So the only part that's going to survive from this sum is xlk. And there's going to be a minus on it, which will cancel with that. So you get a plus, yada, 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 sigma theta inverse IL. This thing survives as is. This is this term here. And then you have the xlk. Now, if we do the other term, it's going to look exactly the same, but what's going to survive is xik. So this should be essentially the same as this expression. And then if you stare at the expression, these are actually equal to one another. You've just flipped I for L, and since you're summing over both of them from 1 to n, these are actually the same expression. So we can combine them, but make sure we have the coefficient 1 out front. All right, so then it becomes this expression. If I factor out the stuff that doesn't depend on L, that's this. And then you have this part that depends on I and L. And if you stare at this expression, what is this? This is doing sigma theta inverse IL times xlk. So this is matrix multiplication, sigma theta inverse times x, because we're summing over the columns here and the rows here. And then we're pulling out, this is going to be a n by p plus 1 matrix. We're pulling out the ik entry of that matrix multiplication. So I'm representing this scalar here as the ik entry of this matrix multiplication. If we look at this thing, this is just the ith entry of y minus xb. So this is the ith entry of this vector. And then we're summing over I. So this is like the dot product of that vector with the kth column of this matrix product. So we can write out the whole thing. It's the dot product here, and we're just pulling out the kth column here. So this is going to be the kth entry of this 1 by p plus 1 vector. Now if we take, so that was for the partial derivative with respect to b sub k. If we take all of them, b sub 0 up to b sub p, and stack them in a vector, we can represent all of the partial derivatives in this matrix multiplication equation. So here, this is the transpose of all this stuff, because this thing actually is a 1 by p plus 1 vector. So I'm going to take the transpose to compare it to this vector. So it becomes x transpose sigma theta inverse transpose, and it's symmetric, so it just stays as is, and then transpose of this. So the partial derivative vector is equal to x transpose sigma theta inverse y minus xb. Now, to get the estimates of the regression coefficients, we set this partial derivatives to 0 and solve for b. So that's what we're doing here, setting it to 0, plugging in b hat, that's the solution. And then we get, if we separate things out, put one side on the right, one on the left, we get x transpose sigma theta inverse y equals x transpose sigma theta inverse x times b. So this equation is the same as this one, just rearranged, which means that b hat equals x transpose sigma theta inverse x inverse, so take the inverse of this part, and multiply it by x transpose sigma theta inverse y. This is what we call the generalized least squares estimate of b. This is the estimate we use when the formula we use when we have a general covariance matrix for the responses sigma theta. Now, just to show you that this is something reasonable, if we plug in sigma squared I, which is the assumption we've been making about the covariances that we've been making for most of the semester, and just evaluate this expression, what you're going to get is a 1 over sigma squared I here. So this is just going to be 1 over sigma squared x transpose x inverse. And you'll get a 1 over sigma squared I here. So this is just going to be 1 over sigma squared x transpose y. That 1 over sigma squared is going to pop out as a sigma squared because we're taking the inverse of that. So the sigma squares will cancel, and you get back to this familiar expression, which is just the solution to the normal equations that we're used to, x transpose x inverse x transpose y. So this is the least squares estimate. So the generalized least square is truly a generalization, because when you plug in sigma squared I for sigma sub theta, you get back the expression that we're all used to. So just to show you what we mean by theta. Theta is a parameter or vector of parameters. So in this specific case, theta is the parameter sigma squared. All right, now let's go back to that example where the covariance matrix was sigma squared times a diagonal matrix, where this diagonal matrix are x1, diagonal of x1 squared up to xn squared. So this is the situation where the variances were different for each observation, and they depend on some covariate x1 to xn. And then we're going to make the other simple assumption that x, the design matrix, is just a column of ones. So this is the exact same example we saw before. Now if we use this generalized least squares formula, plug in the matrix here, we get x is 1, so 1 transpose sigma squared d inverse 1, yada yada yada, 1 transpose sigma squared d inverse y. Now the inverse of sigma squared d is just going to be 1 over sigma squared times d inverse. And d inverse is going to be diagonal 1 over x1 squared up to 1 over xn squared, because it's a diagonal matrix. So you're going to get a 1 over sigma squared pulled out here, and then you're going to get a 1 over sigma squared because there's another inverse. So that's where this sigma squared comes from. and so you have D inverse there. Here, this is just a 1 over sigma squared times D inverse. So that's this one. So these two cancel. And you're left with this expression. Now, if we evaluate this expression, what happens? So D inverse times 1, that is just a vector where the ith entry is the diagonal values in D. So this is going to be a vector, this D inverse times 1. This is a vector where you have first entry is 1 over x1 squared, second entry is 1 over x2 squared, so on and so forth. And then you do 1 transpose times that vector. You're just summing them up. So that's what this thing is. And then we're taking the inverse of this, what ends up being a 1 by 1 matrix. So that's just the reciprocal of this scalar. So this part here is this part of the formula. Now, this part here, we're going to have D inverse times y. So this just ends up being a vector where the first entry is y1 over x1 squared. Second entry is y2 over x2 squared. And then you do 1 transpose that, which just means you add them up. So that this part of the expression is this here. So sum yi over xi squared. So this is the formula for the weighted least squares estimate of B0, where the weights are given by these diagonal entries of the covariance matrix. So one exercise for you would be to show that this actually is an unbiased estimate of B0. So you can use this expression to show that that's an unbiased estimate of B0. So you can do that as an exercise. Now, in this specific case, we were able to write down a formula for what the maximum likelihood estimator of sigma squared was. So we saw that up above. In other cases, and I'll say most cases, sometimes there'll be a parameter that you can write down a formula for, but for other parameters, there's really no formula you can write down. So we actually have to do the optimization. So you don't, it's not like you take the derivatives, you solve the equations, you get a formula for the answer. You actually just use the likelihood, plug it into some optimization procedure. For example, in R, there's something called optim, to numerically find the maximizer. And there's various algorithms for doing that. Kind of the state of the art is Newton-Raphson, but there's also like gradient descent, BFGS, other things as well. So Nelder-Mead is the default in optim. And what we're going to do in the next set of notes, we're going to look at different types of models for sigma sub theta. And for some of them, we're going to be able to write down expressions for the maximum likelihood estimates of theta. But for others, we're not. So we're just going to say plug it into optim and get an answer. Now, this next thing is actually really cool. This is one of my favorite ideas in all of statistics. So it's something called residual maximum likelihood, or frequently you hear it called REML. And this is especially cool because this idea was discovered at Cornell by a guy named Charles Henderson. So one of the things I mentioned before is that one of the problems with maximum likelihood estimates for the variance parameter is it gives you estimates that are biased. And the solution to that is to use the unbiased estimator that we derived earlier in the semester. But residual maximum likelihood, which is also sometimes called restricted maximum likelihood, I prefer the term residual. I'll explain why. Offers a clever solution to the problem that maximum likelihood estimates give you biased estimates of the variance parameter. So if we look here, we worked out that the maximum likelihood estimator for sigma hat squared, in the case where we had independent errors all with the same variance, is you just take the data minus the fitted value, square it, add it up, and divide by n. So this is a residual sum of squares divided by n, and this was the maximum likelihood estimator for that choice of covariance matrix. Now, the estimate we derived before was this one, where it's the same thing, except you divide by n minus p minus 1. And we used that estimate because it's unbiased, and we worked out why that's the right unbiased estimator, and has to do with the dimension of vector spaces and so on and so forth. So for this simple model where the errors are independent, all have the same variance, we can figure out what the unbiased estimator is. But when we go to more complicated covariance models, covariance is for the responses, it's not going to be so clear how to work out what the unbiased estimators are. And so what REML does, it offers sort of a clever way to generate estimates of covariance parameters that in these simple cases, it gives you back the unbiased estimators that you're used to. But for more complicated cases, doesn't suffer from this problem that you're using the data twice to get estimates of the regression coefficients, and then using the data again to get estimates of the variance parameters. So the main idea is the following, if I can sum it up in just one sentence. The main idea of REML is you take the data vector y and you transform it to another vector that has expectation 0 no matter what the regression coefficients are. So you just take your data vector, do a linear transformation, and you pick a specific linear transformation so that the expected value of the transform vector is 0 no matter what b is. This is convenient because now we can use this transform vector to estimate variance parameters, and we never had to actually estimate what the regression coefficients were, which we do at the end. So in a formula, it works like this. So you have your data vector y. Here I'm writing it as the model for the data. And you do z equals m times y. This is what I mean by a transformed vector. We find some matrix m and multiply it by y to get z. But we're being very careful about how we pick this matrix m. We're picking it so the expected value of z, which in this case, using the formulas for expected values, is m times x times b, is 0. So we're picking m so that this is true. And we're picking it specifically so it's true no matter what b is. So it's not going to depend on what the actual value of b is, so we don't have to estimate it first. Then we just use the likelihood for z. Z is another random vector, but z has mean 0, and we use the likelihood for z to estimate theta. All right, so the first question you probably have is, how do we find such an m, such that if you multiply mxb, you always get 0? So let's think about this. Basically, what we need to do is find a matrix m such that mx, so m is n by n, x is n by p, or p plus 1, I guess, doesn't really matter, is equal to 0. If that's true, if you do mxb, you're doing 0 times b, which will always be 0. So we've got to find this matrix m such that mx is a 0 matrix, so that whenever we multiply the 0 matrix by b, we automatically get 0. And the solution to this is to use projections. So if we define the projection matrix P, x transpose x inverse times x transpose, this is the projection matrix for x. And then we do I minus p times x. This is going to be I times x minus p times x, so x minus px. P is the projection matrix for x, so projecting onto the columns of x. Therefore, px is x, and we get 0. So if we define m to be I minus p, then we get exactly what we want. So here it becomes z equals I minus p times y. And this, of course, is iy minus py. And py is the fitted values, the random version of fitted values. And so this just becomes y minus the fitted values, which are the residuals. So this is why I like to use the term residual maximum likelihood. I favor that over restricted maximum likelihood because this is really based on forming these residuals. I think it's a good descriptive way to say what REML is doing. So then the procedure is we use the likelihood for Z to estimate parameters. So the likelihood for Z is a linear transformation of a multivariate normal vector Y. So it's also multivariate normal. Its expected value is mxb, which is 0 by construction, if we pick m to be I minus p. And the covariance matrix is m sigma theta m transpose. And since it's multivariate normal, it has the multivariate normal likelihood, and we maximize this thing over theta to get theta hat. And notice that this equation doesn't contain any b's. Doesn't depend on the regression coefficients at all. So this is really nice, but there is one problem. As we studied before, this matrix I minus P is not a full rank matrix. What is its rank? Since it's a projection matrix, its rank is equal to its trace. The trace of I is n, and the trace of P is the rank of P, which is the rank of the design matrix, which is P plus 1. So this implies that no matter what Y is, if we form Z, some of its elements are exactly recoverable given knowledge of the other elements. So that's a complicated way of saying that the span of Z, or the span of M, which is the projection matrix, is smaller than the number of elements of Z. And this implies that the distribution of Z is degenerate. In other words, instead of living in Rn, its distribution is actually concentrated on a subset of Rn, an n minus p plus 1 dimensional subspace of Rn. If all that's a little too abstract, let me show you the practical issue with using this likelihood to estimate the parameter theta. There's a very clear practical issue. One of the terms that shows up is the log determinant of m times sigma theta times m transpose. Now, using the formula for the product of determinants, this is going to be determinant m times determinant sigma times determinant m again, since determinant m is equal to determinant m transpose. So this is twice log determinant of m plus log determinant of sigma theta. And since M is not a full rank matrix, it's singular, its log determinant is 0. And you try to take log of 0, you get minus infinity. So this is a clear practical problem with using this approach, that you get minus infinity. Another one, related problem, is that the inverse of this matrix, M sigma theta M transpose, this matrix also won't be full rank, and so its inverse doesn't exist. So what sounded a bit pretty simple at first, we just used the distribution for Z, actually has a practical problem that we need to get around. And the solution is actually pretty simple, is instead of using the n by n matrix M, which is equal to this projection matrix, we just pick any n minus p plus 1. So n minus p plus 1 is the rank of M. Any n minus p plus 1 linearly independent rows of M. So instead of using M, we subsample the rows, but subsample so that you pick rows that are linearly independent. And so we use M tilde, which is an n minus p plus 1 by n matrix. And we use the likelihood for Z tilde equals M tilde Y. And so Z tilde will have n minus p plus 1 entries. So we're using this smaller vector, and the vector is shrunk by exactly the number of columns in X. And we use this smaller vector to estimate theta. And as long as we pick M to have linearly independent rows, then everything, those practical problems go away. The log determinant of this product is not minus infinity, so we can actually compute this thing. We can't break this up into the product of determinants because this matrix M tilde is no longer square. So we have to get the determinant or log determinant of this matrix product directly. And this matrix, this is going to be an n minus p plus 1 by n minus p plus 1 matrix, this product. And it will be non-singular, so its inverse will exist. So we plug in this thing here with this restricted likelihood. And if we do that, then everything works. So the REML likelihood is really this likelihood here, where m tilde are n minus p plus 1 linearly independent rows of I minus p. A cool thing, which we won't go into, is actually doesn't matter. You might think that, well, will I get a different answer if I pick different rows of M? Because there won't be just one set of linearly independent rows. It turns out that it actually doesn't matter which ones you pick. So what I mean by that is the theta that maximizes this equation will be the same no matter which rows of M you pick, as long as they're linearly independent. So that will give you the estimate of theta. And we didn't have to estimate B in order to get the estimate of theta, but we still want an estimate of B. And the usual practice is to just use those estimates of theta hat, which maximize this residual likelihood, and then do generalized least squares using those estimated parameters theta. So we form this covariance matrix sigma sub theta hat using estimated parameters theta hat, and do generalized least squares with those estimates. And it turns out that these are also unbiased.